Hi, we are students from Group 3.6 would like to present our integrated design project which titled Methanol Production from Catalytic Syngas Conversion. Our presentation today will focus on three parts, which is introduction, reaction engineering and reactor design, and last but not least, conclusion. Today, we will discuss reaction engineering and reactor design with a focus on methanol synthesis. Methanol is not only a clean fuel, but also a key chemical intermediate. Converting CO2 and syngas into methanol has gained attention due to its potential for reducing greenhouse gas emission. The CZA catalyst system remains industrial benchmark, offering high activity, selectivity, and stability under moderate temperature and high pressure. In our process, we utilize an adiabatic multiple bed reactor with interstage cooling, which allows efficient heat management, maximize methanol yield, and preserve catalyst longevity. Today, we will explore catalyst selection, reactor design, kinetics, and strategies to prevent deactivation. The conventional industrial catalyst for methanol synthesis is copper and zinc oxide on alumina, or also called as CZA. It performs very well in terms of activity, but under CO2-rich condition, its long-term stability becomes an issue. This is mainly because the alumina support is hydrophilic, so water tends to accumulate on the catalyst surface. Over the time, this water accelerates deactivation and reduce methanol yield. To overcome this, researchers have explored promoters such as ferrum, palladium, and especially zirconium. Among these, zirconium has shown the most promising result. It acts as a structural promoter by preventing copper oxide and zinc oxide particles from agglomerating and by improving copper dispersion. This enhances the catalyst's resistance to water and slows down irreversible deactivation. Studies have shown that zirconium-modified CZA catalysts maintain structural stability better and resist sintering more effectively. Zinc oxide also plays a critical supporting role. It helps inhibit the formation of inactive copper aluminate phases and increase surface area and pore volume, improving durability at industrial temperatures. Even though zinc oxide slightly reduces initial activity, it increases long-term performance and regenerability. Overall, the CZA catalyst system, especially when promoted with zirconium, remains the best choice for methanol synthesis from CO2. It is active at moderate temperatures, highly selective toward methanol, resistant to thermal degradation, and economically viable for large-scale production.
Hi, my name is Reina. Before I begin, I would like to apologize for my voice. I am currently recovering from a flu, but I will try my best to present clearly. So today I will explain why the adiabatic multiple bed reactor, or AMBR, is widely used in the methanol synthesis loop. Methanol synthesis loop is a highly exothermal process, which means a lot of heat is released inside the catalyst bed. If this heat isn't managed properly, the temperature can rise too quickly and creating hotspots that damage the catalyst and reduce efficiency. So the AMBR design solve this by dividing the catalyst into several adiabatic beds, which within each bed, the temperature rises naturally, and after each stage, the hot gases is passed through an interstage cooler to bring down the temperature back before entering the next bed. So this prevents heat buildup and keeps the reaction within a safe and optimal range. So the multi-bed approach also provides a good balance between reaction kinetics and equilibrium. High temperature inside each bed help maintain fast reaction rates, while the cooler inlet temperatures after each cooling stage shift the equilibrium towards the methanol formation. This combination improves per pass methanol yield while protecting the catalyst from thermal degradation. So to enhance performance, plants may use graded catalyst loading, placing lower activity catalyst in the first bed and higher activity catalyst downstream to spread heat release more evenly. So interstage cooling can be done either through heat exchangers, which can also recover steam, or through quench injection, where cooled syngas is added to quickly lower the temperature. Finally, the recycle loop plays a key role. Unreacted syngas is recycled back to the reactor to increase overall conversion, and this recycle stream also serve as a controllable quench medium. So this give operators flexible temperature control, making the AMBR both safe and efficient for large-scale methanol production.
Today, I will briefly explain the reaction kinetic and equilibrium involved in methanol synthesis. Methanol is mainly produced through two hydrogenation reactions, CO plus H2 forming a methanol and CO2 plus H2 forming methanol and water. A side reaction called the reverse water gas shift converts CO2 and H2 into CO and water. This reaction is important because even a small amount of water can shift the balance, changing the CO and CO2 ratio and affecting the overall methanol yield. Methanol synthesis is exothermic, so lower the temperature favor a higher equilibrium conversion, but higher temperature improve reaction rate. Because of this trade-off, reactors must operate within an optimal temperature range. To manage this, industry use an adiabatic mul- multiple bed reactor. This reactor keep the temperature nearly constant, prevent hot spot, and maintain a good heat removal. It is also supports steady reaction rate and protect the catalyst from deactivation. High pressure also play a key role by shifting the equilibrium toward methanol and increasing per pass conversion, allowing the plant to reduce recycle flow. Larger reactors further improve per-pass conversion, although they increase the capital cost and the benefit eventually level off. Overall, balancing temperature, pressure, and reactor design is essential for maximizing the methanol production.
Hi everyone, we'll continue with the catalyst support properties and longevity. The long-term reliability of our copper-based catalyst hinge entirely on the support structure, specifically the partnership between zinc oxide and alumina. Zinc oxide is the essential structural promoter and spacer. It is critical because it physically separates the copper particles, actively inhibiting sintering or particle agglomeration. This spacing it is what allows the crucial synergistic interaction between the copper and zinc oxide to occur, which determines the catalyst high performance. Alumina, on the other hand, serve primarily as a refractory stabilizer and dispersing agent, ensuring a high initial surface area for the active components. Our design strategies must mitigate the three primary deactivation threats. The first one, sintering, is the loss of specific copper surface area is primary intensity mechanism. We mitigate this at the micro scale by adopting a multi-bed reactor with interstage cooling. This engineering control prevents the extreme temperature, which drive the exponential increase in sintering rates. Second one, water-induced deactivation. Water is the product of methanol synthesis and acts as the potent promoter of copper sintering, disrupting the strong metal support interaction. Future material design must address this by integrating highly stable structural promoters such as zirconium. Lastly, carbon deposition or caulking is generally not a significant issue in the system, but provided we maintain a clean syngas feed with a high hydrogen content. Next, to affirm future catalyst development, we use advanced techniques to characterize the spent material. We divide this analysis to two categories. The first one is the structural and thermal analysis. Reactive natures or side frontal chromatography measures the specific copper surface area. A quantified decline in this directly confirms the sintering as the loss mechanism. HRTM visually confirms this by imaging the copper particle size distribution, revealing the particle growth that is characteristic of the sintering. Second one is the chemical and compositional analysis. Temperature program reduction (TPR) directly probes the chemical reactivity and redox properties of the catalyst. Techniques like XAS and XPS are employed to confirm chemical segregation and the undesirable formation of new inactive phases, such as spinel. This precise measurement allows us to move beyond simple performance loss to definitely isolate the structural disruption and chemical change mechanism. This quantitative data provide the foundation for future catalyst material design, allowing us to iteratively develop formulations that are more resistant to thermal and chemical stress. This will be presented in the next part.
Hi everyone, moving on to the catalyst deactivation characterization. and future catalyst material design. So there are three, which is the first one is stabilize active sites, enhance support resistance, and advanced characterization. So the key objective is to stabilize the active sites. This can be achieved through two main strategies, which is the first one to maximize the initial structural integrity of the catalyst and by using the advanced characterization techniques for deeper insight. For instance, the HRTEM and XRD confirm high copper dispersion and surface area in system where the metallic copper is maintained in highly defective, strained, and non-equilibrium state. So this structural understanding directly informs the design of the next generation catalyst materials where we are aiming to preserve the active sites under reaction conditions and significantly improve the catalyst longevity and also the performance of the catalyst. To conclude, our reactor and catalyst design successfully manage the exothermic nature of methanol synthesis with multi-stage cooling, while the optimized catalyst formulation ensures long-term stability. Looking forward, insights from characterization techniques like HRTM guide future material design. The goal is to increase resistance to thermal stress and minimize structural damage caused by changing metal support interactions. To achieve this, we recommend a four-point plan. First, prioritize rational catalyst design based on microstructure. The second, enhance support stability to fight chemical deactivation. The third one, exploit advanced reaction kinetics for immediate performance gains. And lastly, implement sophisticated process control strategies to maintain the optimal operation.